Hi everyone. So we are starting with the chemical reactions of phenols. Till now we have completed the preparation of phenols. Okay, so in this video we'll be discussing the chemical reactions of phenols with metals. How phenols react with metals we will be discussing in this video. So when phenols are reacted with metals, okay, the metals are active in nature. We can have sodium, we can have potassium, aluminium. Okay, these are the active metals. It means they are reactive metals. So they react with phenols and we get the corresponding phenoxide in the reaction. Okay, corresponding, as in this case we are reacting a phenol with sodium metal, so we are getting the sodium phenoxide. This is sodium phenoxide. Okay, we are getting sodium phenoxide and hydrogen gas in the reaction. So when metals react with phenols, we get the corresponding phenoxides. As in case of alcohols, we're reacting alcohols with metals and we're getting the corresponding alkoxides. Okay, in addition to this, also phenols can react with sodium hydroxide, aqueous sodium hydroxide if we are taking. Okay, and its reaction with phenol will again give us the sodium phenoxide. We'll be getting the sodium phenoxide, and we should remember that this sodium phenoxide is a very useful precursor for the preparation of many organic molecules. Okay, and in this reaction we are getting water as a byproduct. But how we can explain this reaction? If you look at the reaction and what changes are taking place in the reaction, you look that there is the removal of this hydrogen. In both the cases we are removing the hydrogen, and the hydrogen is removed, and in that place where the corresponding metal is substituted. So this means the phenol is losing the proton. It's losing the proton, and therefore it's a good acid. Although it's weak acid, but it is an acid and a good acid and better acid than an alcohol. As we had discussed the acidity of alcohols, we discussed that alcohols are weak acids, but we have to remember the alcohols are weaker than the phenols, very weak acids than the phenols. So in this case also the phenols are losing this proton. They are losing this proton. As a result, they become the acids. But the question arises, why do they lose the proton? Okay, so to understand this, we'll look at the structure of the phenol and its hybridization. Okay, so if we take a phenol, we have a phenol. This is a phenol molecule. Okay, we have lone pairs of electrons on this oxygen. So there is, because this hydroxyl group is directly attached to the sp2 hybrid carbon of this benzene ring. Okay, of this benzene ring. As a result, these lone pair of electrons present on the oxygen, they are capable of delocalization. They are capable of showing delocalization, and that's they can easily move around this ring. Okay, as a result, we are getting different hybrid structures of this phenol. Okay, so let's check the different hybrid structures. So what's going to happen? This lone pair of electrons will move to this bond, and there will be the formation of a pi bond between the oxygen and the carbon. Okay, oxygen and the carbon, and this pair of this pi bond will be broken, and the lone pair of electrons will shift to this carbon. As a result, there will be a negative charge on this carbon, and now this pi bond is broken. And there is double bond between carbon and oxygen. Okay, and we have hydrogen. So there is a positive charge on oxygen in this structure. What's going to happen in the next stage? Now again this will shift. This lone pair of electrons will shift, and there will be formation of a pi bond between this carbon, and this pi bond will break, and we'll be getting another hybrid structure of phenol. So there is double bond between this carbon and this carbon, double bond between oxygen and positive charge on the oxygen, and we have a negative charge, and that's a lone pair of electrons is shifted to this carbon. And again in the similar way we'll be getting another hybrid structure. That will look like this will be shifted, and the pi bond will be formed between this carbon with a negative charge on this carbon. Lone pair of electrons will shift here, and double bond between carbon and oxygen, and again we have a positive charge on the oxygen, and again then this will show the arrows. Okay, now this lone pair of electrons is going to shift. This will kick off this lone pair of electrons up to the carbon, up to the oxygen, and we'll be getting the final hybrid structure. That is, we'll be having a oxygen, hydrogen, and this is the, so in this case we are having 1 2 3 4 and 5 hybrid structures of this phenol. Although this fifth one and the first one are the same, we can also say that there are 4 hybrid structures. Okay, in at many places we'll see that it's written that it has only 4 hybrid structures, and in many places we'll see that it has the 5 hybrid structures, but it's not going to affect us. Okay, so these are the 5 hybrid structures of phenols. So these much of hybrid structures shows us that the phenol is enough, it's enough stable. But the question arises, why, if it is stable, why then it is losing this proton? So the answer lies in the question, because the overall change that takes place is we have a phenol when it loses a proton, it gives us the phenoxide ion. We get the phenoxide ion. Okay, we get the phenoxide ion plus hydrogen, H positive proton. Okay, so we'll also look at the hybrid structures of, because this lone pair of electrons on the oxygen is again capable of delocalization. Due to this delocalization, there will be some stability. There will be stability in this phenoxide ion as well, and we'll be looking at the hybrid structures of this phenoxide ion. So this is the phenoxide ion. We have oxygen, and there is lone pair of electrons on this oxygen. So what's going to happen? These lone pair of electrons will be delocalized. As a result, this pair of electrons will transfer to this carbon, and we'll be getting the hybrid structure having a negative charge, a lone pair of electrons on this, and there is a double bond between carbon and oxygen. Okay, now in next structure, what will be happening, will be getting like this. So this will be shifted to this, and this lone pair of electrons will shift to this carbon. Now the negative charge is on this carbon, and the double bond is between this carbon. Okay, and we have the rest structure is same. Okay, now again this pair of electrons will delocalize, and this will break, and the electron will go to this carbon, and the next hybrid structure that will be getting will be a negative charge at this place, pi bond, and double bond between carbon and oxygen. Now again this will shift, and this will go there, and we'll be getting our final structure, that is the initial phenoxide ion. So what's the difference between these two, with the hybrid structures of phenol and the phenoxide ion? If we look at the hybrid structures of phenol, then there is a positive charge on the oxygen. In 3 hybrid structures, there is positive charge on the oxygen, and there is a charge separation. In this case, there is charge separation. There's charge separation in this case. That means in these 3 structures we have positive charge as well as negative charge. Okay, and in this case there is nothing like the charge separation. Okay, there is no charge separation. You can look that in all the hybrid structures we have only negative charge. present. So in this case we have delocalization 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 of only the negative charge. So in this case only negative charge is delocalized, and in this case we have charge separation. Thus if we compare the two, then this is less stable as compared to the phenoxide ion. So the phenol is less stable, so we can conclude that phenol is less stable than the corresponding phenoxide ion. What is the reason? The reason is that in the case of the phenol there is charge separation, making it less stable. This positive charge present in these three hybrid structures makes the phenol less stable. Okay, and the delocalization of negative charge in case of phenoxide ion makes it more stable. So this phenoxide is more stable than the phenol. So in this case the forward direction, this reaction will be favored, and the backward reaction will not be favored. So this is the reason why phenol is acidic. So it easily loses the proton. This proton is easily lost. Why? Because it's going to give us a more stable phenoxide ion. So stability is the factor. So when this phenoxide ion is stable, so the formation of phenoxide ion in this case will be favorable reaction. Okay, so that's why it loses the proton easily and hence is acidic in nature. Now if we compare the acidity of different groups, different acids, so what we looked at, if we talk about if we look at the carboxylic acids are more acidic than phenols. They are more acidic than phenols, and phenols are more acidic than water, and water is more acidic than what you call as alcohols. So there is a difference in the acidity, large difference in the acidity of phenols, between the acidity of phenols and the alcohols. If we compare the pKa values of these particular acids, then the pK value of carboxylic acid is 5. pK value for phenols is 10, for water is 14, and for the alcohols it is 18. Okay, so this pK value shows the difference. There is a large difference between phenols and the alcohol acidity. Okay, and this difference is why because there is the stability. The phenoxide ion formed in case of phenols is more stable than the alkoxide ion that's formed in case of alcohols. What I mean to say is, if we talk about an alcohol, when alcohol ionizes, it gives us a alkoxide ion and a proton. And when a phenol is ionized, what we get a phenoxide ion. And in this phenoxide ion, the negative charge on this carbon is in conjugation with this benzene ring, which makes it more stable. So that's why the phenols are more acidic. They can easily lose this proton as compared to the alcohols. And if you talk about this reaction, this reaction is favored in the backward direction. Okay, backward direction is favored in this case. Okay, and we can also there is also the effect of presence of groups on the acidity of the phenols. So the presence of groups on the phenols also alters the acidity of, it disturbs the acidity of a phenol. So if we talk about phenol, if this phenol is substituted, for example, there is a group G present on the phenol. If this group G is electron withdrawing group, then it's going to increase the acidity. Of the phenol. And if it's electron donating group, if this group G is electron donating group, then this is going to decrease the acidity of phenol. For example, if we take the example of electron withdrawing group, we have NO2 group. If we take the example of electron donating group, we have a methyl group, for example, CH3. So CH3 group is going to decrease the acidity of the phenol, and electron withdrawing group is going to increase the acidity of a phenol, because this if we have a presence of electron withdrawing group, so it's going to pull the electron density of this ring towards itself. As a result, the electron density on this oxygen is decreased, which polarizes the oxygen hydrogen bond. As a result, its breakage is easy. And if we have electron donating group present in the ring, then it's going to increase the electron density of this oxygen, making the oxygen hydrogen bond less polar. As a result, the abstraction of a proton from the oxygen is not too easy, making it less acidic in nature. Okay, so we have to look at this thing. So in the upcoming videos we'll be discussing other reactions